Imagine a world where every ray of sunlight is captured and transformed into clean, renewable energy. This isn't just a dream of the future, it's the reality of today, thanks to the incredible technology of solar panels. These devices, often seen gleaming on rooftops and sprawling across fields, are at the forefront of our battle against climate change and our quest for sustainable living. But how exactly do these panels work? Let's dive into the fascinating science behind solar panels. At the heart of a solar panel lies the photovoltaic or PV cell, the fundamental unit responsible for converting sunlight into electricity. The term photovoltaic combines the Greek word photo, meaning light, and voltaic, referring to electricity, which perfectly encapsulates the essence of this technology. A typical solar panel consists of many PV cells made primarily from silicon, a semiconducting material abundant in nature. Silicon, in its pure form, is not very efficient at converting sunlight into electricity. Therefore, it's doped with other elements to enhance its electrical properties. This doping process introduces impurities into the silicon, creating two distinct layers within the PV cell, the N-type layer and the P-type layer. The N-type layer, infused with phosphorus atoms, has an excess of electrons, while the P-type layer, doped with boron atoms, has a deficit of electrons, creating holes. When these two layers are brought together, an electric field is formed at the junction between them. This field acts as a barrier, preventing electrons from moving directly from the N-type layer to the P-type layer. Instead, it sets the stage for the photovoltaic effect. The photovoltaic effect is the process by which sunlight is converted into electricity. When photons, which are particles of light, strike the PV cell, they transfer their energy to the electrons in the silicon atoms. This energy boost allows the electrons to break free from their atomic bonds and move. These free electrons are then pushed towards the N-type layer by the electric field at the junction, creating a flow of electrons. This flow of electrons is essentially an electric current. To harness this electric current, metal conductive plates are attached to the PV cell. These plates collect the electrons and transfer them to wires, creating a usable electric current. This current can then be directed to power homes, businesses, and even entire communities. However, the direct current, or DC, produced by solar panels is not compatible with most household applications, which require alternating current, or AC. This is where inverters come into play. Inverters are devices that convert the DC electricity generated by the solar panels into AC electricity, making it suitable for everyday use. One of the most remarkable aspects of solar panels is their ability to function under various conditions. While they perform optimally in direct sunlight, they can still generate electricity on cloudy days. This is because PV cells can capture diffuse light, which is scattered sunlight that reaches the Earth's surface even when the sun isn't shining brightly. Although the efficiency of solar panels drops under these conditions, they still contribute to the energy supply. The efficiency of solar panels, or the percentage of sunlight they can convert into usable electricity, has been a significant focus of research and development. Early solar panels had efficiency rates of around 6%, but modern panels can achieve efficiencies of over 20%. Advances in materials science and engineering continue to push these limits, with experimental technologies exploring efficiencies beyond 40%. Moreover, solar panels are not limited to traditional flat installations. Innovations like bifacial panels, which capture sunlight from both sides, and flexible panels, which can be integrated into various surfaces, are expanding the possibilities for solar energy development. Additionally, solar tracking systems, which adjust the orientation of panels to follow the sun's path, can significantly enhance energy capture. The environmental benefits of solar panels are profound. Unlike fossil fuels, solar energy produces no greenhouse gases or air pollutants during operation. This means that widespread adoption of solar technology can significantly reduce our carbon footprint and help mitigate the effects of climate change. Furthermore, solar panels require minimal water for maintenance, making them a sustainable choice even in water-scarce regions. Economically, solar panels offer long-term savings on energy bills and can even generate income through net metering, a system where excess electricity produced by solar panels is fed back into the grid, earning credits or payments for the producer. While the initial investment in solar panels can be substantial, government incentives and declining costs of PV technology have made solar energy more accessible to homeowners and businesses alike. In summary, solar panels represent a marvel of modern technology, transforming the abundant energy of the sun into clean, renewable electricity. Through the intricate interplay of materials science and engineering, they harness the power of photons to generate electric currents, providing a sustainable solution to our energy needs. As research and innovation continue to advance, the future of solar energy looks brighter than ever, promising a greener and more sustainable world for generations to come.